Question number 3 started out as an electrochemistry kind of question. We need to complete and we need to label. Even when the question doesn't say label, you've got to label. And this is under standard conditions, so make sure you write down the standard conditions at some point. This is standard cell potential. Cell potential. So no standard hydrogen electrode because the cell here is between chlorine and chloride. So that is your non-metal. Non-metal. And that is your non-metal ions. If you have non-metal and non-metal ions, they cannot conduct, which is why they provide us this thing here. This is platinum electrode, which means this must be the chlorine gas. Chlorine is a gas at room temperature and pressure. This is 1 atm pressure because gas have pressure, and I can just write down this as 298 Kelvin or 25 degrees Celsius for the standard conditions there. Of course, I also have my solution, which is 1.00 mole per dm cube Cl minus aqueous. Okay. Now I've got to draw the other side. This is going to be the metal. Actually, this is metal ion. This is metal ion and metal ion. So I don't have the metal as the electrode. Instead, I would have platinum electrode as well. I need an inert electrode because this electrolyte here is going to be equimolar. So equimolar, Fe2 plus aqueous. Actually, I forgot the 1.00 mole per dm cube. 1.00 mole per dm cube iron 2 plus. And also 1.00 mole per dm cube iron 3 plus aqueous. And we want to calculate standard cell potential, so we need a voltmeter. A voltmeter will measure the potential difference, but our circuit is not complete, so I need to draw a salt bridge in order to complete the circuit there. So what do I have? I have my electrolyte here, which consists of equimolar mixture of these metal ion and metal ion. Already specified the standard condition concentration there. I already specified the other standard conditions, and this is a chlorine gas and the chloride solutions. As this is a non-metal and non-metal ion system, we also need a platinum electrode there. The salt bridge complete the circuit, and my diagram should be alright for that easy 4 marks there. Now use the data booklet. Again, in the new syllabus, in the new 2022 specifications, the data booklet is no longer a separate booklet. It is now inside the question paper itself, where you'll be given the data. So by looking at this, you have to choose carefully. This is iron 2 going to iron 3. So that is your oxidation. So you will see in the data booklet or whatever data you're provided, you have to choose the one that looks like this, iron 3 going to iron 2. Because reduction potential is always shown as reduction. So electrode potential is reduction potential. Reduction potential always show reduction. So I'm on the data booklet. Iron 3 plus going to iron 2 plus is plus 0.77 volt. We know that it's not the iron 3 plus that we started reacting with, it's the iron 2 plus. So we know that this is our EOX. We don't change the sign because it's already included in the working, in the formula that I'm going to show you in a little bit. And the other equation will be the Cl2 plus 2 electrons going to 2 Cl minus. That thing in the data booklet shows me as plus 1.36 volt, and that is my E red. So what I'm going to do now is I'm going to copy paste that onto this thing here. So obviously, you know, with the data booklet, you don't really have to write anything. I'm just showing you because I don't have the data booklet shown in front. I just have my data booklet on the screen. So my E cell equal to E red minus E ox. And that is equal to plus 1.36 minus bracket plus 0.77. Even though we are showing the oxidation, we already label it. We do not change the sign. It's already included in the formula itself. When you do this on a calculator, your calculator will show you 0.59, and that is not actually correct because you are missing the sign, which has to be, you know, shown as stated in the whole of data booklet. All the electrode potential has plus or negative, except for 0.00 for the standard hydrogen electrode. So this is greater than 0, so this reaction is feasible and spontaneous there. Okay. Now, what color change? Color change. So not just what you will see at the end. It means from what to what. When you bubble chlorine gas into this solution, they contain iron 2 plus until the reaction is complete. This is iron 2 plus aqueous. This is not iron 2 hydroxide. This is a green precipitate. This is a pale green solution. So the pale green solution, which coincidentally is also the color of chlorine gas in solution. So, the color can kind of overlap due to the chlorine gas, which is pale green, or also due to the iron 2 plus, which is actually slightly darker pale green than this chlorine gas, depending on their concentration, of course. So what that turns into is, it would turn into the iron 3 plus. So this thing is colorless, but the iron 3 plus is iron 3 plus surrounded by 6 water. So it is not the precipitate, but it's kind of like a orange brown solution. So it's got a slightly darker kind of color. So yellow orange kind of solution. So previously it was kind of green kind of ish solution, whereas now it's more orange yellow or more of like a red orange kind of solution. But what it is not, do not get confused with iron 3 hydroxide versus Fe3 plus aqueous. This is one thing that a lot of students get confused about. On top is when you have alkaline environment, you only have water, you don't have alkaline environment here. Now the next bit is to do with Le Chatelier principle as stated in AS chemistry under equilibrium. So Le Chatelier principle states that for a system in equilibrium, if you introduce a change to a system in equilibrium, that system or that equilibrium will try to oppose the change, counteract, go against the change so that you go back to equilibrium. Now predict the effect, if any, and then explain your answer. What is the effect of decreasing the concentration of Cl- on the cell potential? Okay, let's have a look at the overall equation. The overall equation looks like this, but it's actually in equilibrium. That's why these are called redox equilibrium. So I'm just going to write this down as an equilibrium, and then we will try and consider it at the bottom when we see the equations. So we know that this equation here, is that a good idea? Let me change the color so that it is much more visible. So we know that explaining our answer is going to be the second bit of the question that we need to answer. So that thing there is E cell equal to plus 0.59 volt. So this is actually part of the new syllabus introduced from 2016. They call it the Nernst equation. But the Nernst equation is a quantitative, it's to do with numbers. This got nothing to do with numbers, so we don't really need to think about the actual calculation. So what I can do is I can explain first. Alright, so as the concentration of Cl- decreases, so this thing in a square bracket represent the concentration of Cl-, as that decreases, what would the equilibrium tries to do? The equilibrium will try to increase the concentration of Cl-. How can I increase the concentration of Cl- to counteract the change? I will shift to the right. So therefore, I will shift to the right side to form or to produce more Cl-. As I shift to the right hand side, therefore, when I shift to the right hand side, therefore, my E cell will become more positive. As I become more positive, the reaction become more feasible. They just say what is the effect on the cell potential. As you shift to the right hand side, you will favor the right hand side, and therefore the E cell will become more positive. This is the overall redox equation, so I cannot say it favors just the reduction. In fact, it does favor the reduction more, as it favors the Cl2 going to Cl- to increase the concentration of Cl-. Having said that, your E-rate will become more positive, but it's no longer standard. If your E-rate become more positive minus the same value is going to give this more positive. Or you can look at the whole picture. When the whole thing shifts to the right, your E cell will become more positive, and you can confirm this with the Nernst equations as stated in the new syllabus. You can confirm with a couple of values. above 1.00, when actually below 1.00 when you decrease the concentration of Cl minus with that Nernst equation. So I've just answered the first bit to the question by answering the explanation first in terms of Le principle, and I still get the effect to answer the first bit of the question. That's how I get the 2 marks there. Now just a few more questions to run up this electrochemistry bit. So a fuel cell, so we know a fuel cell is a clean energy. In this alkaline fuel cell, so not acidic, yeah, alkaline fuel cells, so we have OH minus, not to do with the acidic conditions. Write the half equations. So these are straight from the data booklet. I'm not sure how useful it will be when you don't have the data booklet in front of you, because that's how it is in the new paper, in the new syllabus. So what we have there is hydrogen. They are passed over 2 inner electrons immersed in alkaline conditions. So realistically speaking, what kind of thing are we looking at? We're looking at OH minus. I know we're looking at one of these, so O2 plus 2H2O plus 4 electrons going to 4 OH minus. You might have seen that from your O-level or IGCSE days. And the next one will be something to do with hydrogen, I guess. So where's my hydrogen? Yep, I found one. So the one they're looking for is not the H plus electron going to hydrogen gas. You're actually looking for this other one, which is 2H2O plus 2 electrons going to the H2 plus 2 OH minus. But then both of them show reduction, so that is not exactly true. What happened? I guess the hydrogen and the oxygen has to react. So this hydrogen plus 2 OH minus should be on the left hand side because the hydrogen is the reactant in the fuel cell. So that means you will get that, and that is actually your oxidation, loss of electrons. I've just reverted the equation shown in the data booklet as part of reduction potential. So the hydrogen and oxygen will combine. This is 2 electrons, this is 4 electrons. If you multiply the whole thing by 4, you will get 2H2 plus 1 O2. And then the 4 OH minus on the left, cancel the 4 OH minus on the right. This will be multiplied by 2 to give you 4 H2O on the right, 2 H2O on the left. Overall, you will get 2 H2. If you multiply the first bit by 2 and then you add with the second bit, you get 2 H2 plus O2, giving you 2 H2O. This is the overall fuel cell reaction, which is basically the hydrogen combined with oxygen in order to, give you the clean energy. Because there is no other pollutant. So one possible advantage over a conventional simple cell battery. Okay, we need to be careful here because a simple cell battery does not give carbon dioxide. So we can't talk about that this is a clean energy and no pollutants because this thing doesn't give out carbon dioxide as well. So it's a suggestion question, but then you can't possibly use the idea of clean energy here because of what a simple cell battery does. It's one of those batteries that they have in laptops and stuff that feed on electricity. So I guess what do we think about here? Oh wait, hang on. This simple cell battery wouldn't be those rechargeable battery. This is probably one of those disposable AAA or AA battery. So in a sense that those are disposable and they might not last very long as compared to a fuel cell, which of course is used in a rocket, not just rocket, in space shuttle as well, because that's how they sustain life out there in the space for the astronauts. Okay, so obviously this is talking about longer time between recharges because longer time before having to recharge fuel cell because they can last over a longer time. They have a bigger energy storage capacity compared to a simple cell battery. Bigger energy density, I guess, energy storage capacity or energy density compared to a simple battery, compared to simple cell battery. Okay, I'm sure there are many other more advantages that you can think of. These are just one of the things that come on top of my mind really. Okay, so that's it really for this 12-mark electrochemistry question.